Permutation testing procedures provide a way to perform exact inference. These testing procedures are used in a wide variety of areas to do a wide variety of different tests. We are going to look at how permutation tests can be used for one specific type of test, the testing of independence in a contingency table. Now, to motivate how permutation tests come about, let's take a look at this particular example. This goes back to the lady tasting tea experiment that we saw previously. And we saw this table where we had this distribution of M, which ended up being the number of times that the lady said that milk was poured first, and it truly was poured first. We had then the corresponding probabilities that came about from the hypergeometric distribution. And then we also had the estimated odds ratios for each of the possible contingency tables. Now what I've done is added a column that includes the Pearson chi-squared test statistic. Using this column, notice, or taking a look at this column, notice we have some duplicate values. So if we want to find the actual or exact probability distribution for this Pearson statistic, all we would need to do is sum over these like values of these x squares, sum over the corresponding probabilities. So the actual exact distribution for x squared is what I show here. So probability x squared is equal to 8 is 0.0286. With that then, we can go ahead and plot then the cumulative distribution function for x squared. And we can also look at the cumulative distribution function for a regular old chi-square random variable with 1 degree of freedom. Of course, the chi-square random variable is a continuous random variable, where here x squared only has 3 possible values. And so what we see here in these plots of these CDS are some large differences. And so think about what this means in terms of using the Pearson chi-squared test statistic in this particular case to test for independence. We're using a continuous distribution to make a judgment about a discrete distribution that only has 3 possible values. As you might imagine, this approximation may not work out very well. Now, a permutation test for independence uses essentially this exact distribution to calculate p-values. So for example, if x squared was observed to be 2, then the probability of being at least this extreme relative to the probability distribution would be the probability that x squared is greater than or equal to 2. If you add up those corresponding values, you get 0.4858. Now, when the sample and or the contingency table is larger than what we had here, we're not going to be able to simply use a hypergeometric distribution as we just did there to help calculate the exact distribution for x squared. Rather, what we're going to need to do is actually simulate this distribution using Monte Carlo simulation and use some of the same kinds of methods that we saw back in chapter 3 when we did a Monte Carlo simulation test for independence. In particular, for example, for a large number B of contingency tables, so we're going to simulate B contingency tables under the null hypothesis of independence. For each contingency table, we're going to calculate x squared star. And maybe we repeat this B equal 1,000 times. If I do a histogram of all these x squared stars, that gives me then a good estimate, since B is large, a good estimate of what the actual probability distribution is for x squared. And so based upon that, we can calculate a p-value such as the number of x squared stars greater than or equal to the actual observed x squared with the original data. That all divided by b, so I can get a proportion that are larger of the proportion of x squared stars that are larger than x squared. That will give me my p-value for my test of independence. Now, we're not doing exactly what we did in chapter 3. In chapter 3, what we actually did was essentially we simulated these contingency tables assuming the row totals were fixed. Now what we're going to do is assume the row totals and the column totals are fixed to do this simulation. So to help see how this is done, let's go back to the lady tasting tea example once again. So here's this hypothetical situation that we looked at involving the lady tasting tea. And I've added a 1 and a 2 here to help us say row 1, row 1, row 2, column 1, column 2 corresponding to the lady's responses and what actually happens. We could put this data into a raw data format. We actually looked at that a little bit before when we first were looking at the Larry Bird data set in terms of how we would actually observe the data. You know, you have a column for the first free throw attempt, and you would have written in that column made or missed corresponding to one observation. Then the second column would be the second free throw attempt, made or missed. And we have the same number of rows then in this raw data format of the data as the same number of rows as were the same number of free throw pairs that were shot. Let's put then the lady tasting tea data here into that raw format. So let me remove that break there. So the first table here is what we have displayed here. This is, let's say, the original set of responses. So to help us see what's going on, we have row 1, column 1, row 1, column 1, row 1, column 3. It's hard to say this sometimes. And so what we see here, we have 3 times we have a combination of row 1 and column 1. That's why I have the 3 there. But I want to make sure that I differentiate between maybe the first cup, the second cup, and the third cup that fell into that particular cell. So because of that, that's why I decided to put this label of Z1, Z2, Z3 there. Then we also have 1 cup here for row 1, column 2. So let's have row 1, column 2, and so on. And so again, the Z's there are meant to help us differentiate, let's say, the different cups in a particular cell. Lastly, just to make sure we see this, because it is important, notice how I have 3 there. So Z6, Z7, Z8, they are exactly the same values. Okay. Now, if we had independence between the row variable and the column variable, what that would say is that these column responses could fall into any order relative to what we have for the row responses. Perhaps, for example, we simply change Z1 and Z2. This will lead to the same contingency table, but under independence, essentially, every possible permutation of these column numbers would be equally likely. Here's another example. Suppose we change a few more things around. So we change that one, this one, and this one. Okay? Again, under independence, all these column designations in terms of the Z's would be equally likely to occur with the corresponding row numbers that we see there, because there's independence. Column doesn't depend upon what happens with a row. So what we have here are, you could say, 3 different permutations of the data, where the first 2 here lead to an x2 equal to 2, and this one, x squared equal to 2, and this one leads to an x squared equal to 0. Well, why? Well, notice how I have, for row 1, I have 2 column 1s. For row 2, I have 2 column 2s. Same thing happens. Let me restate that to make sure I got that right. For row 1, I have 2 column 1s. For row 1, I also have 2 column 2s. I have the same thing happening with row 2 as well. That's why I have an x squared equal to 0 there. You can do the calculations on your own just to prove that. Okay, let me move on. Okay, so just to emphasize, under independence, the row numbers and the column numbers are equally likely to be paired up. Thus, we can mix up or permute the row numbers and also do the same for the column numbers to obtain one possible contingency table that would be equally likely to occur under independence. Now, because the total number of 1s and 2s is fixed for both the row and column variable, we can actually just simply permute the column variable. That would be good enough. And since there are 8 possible rows to this raw data format, that means there are 8 factorial or 40,320 different permutations of those column numbers. Each of them are equally likely to occur under independence. Now, as we saw, some of the corresponding contingency tables of these 40,320 will be exactly the same. That's fine. But they do represent distinct different permutations that can occur. So we saw this up here, where these 2 raw data formats result in the same contingency table. And so if we wanted to, then we could actually do this 40,320 times. And if you did, you will notice that 20,736 of them lead to an x squared of 0. Now, did I actually do 40,320? No. But the reason why I know this is because we can go back to that hypergeometric distribution. We know what the corresponding probabilities for the x squared equal to 0. And based upon that probability, then I can figure out, okay, that means then how many I would have to have 20,736 of these 40,320 to produce that probability that we saw in that previous table. Okay, so you can see if I were to do all possible permutations here, that could potentially take a long time. So instead, what is done is a large number of permutations, so we'll call it B, maybe B might be 1,000 or 10,000, will be done in practice. And that is what's going to give us what's called our permutation testing procedure. So here's the algorithm that one could use to do this process. Step 1, randomly permute the column numbers while keeping the row numbers unchanged. Step 2, calculate my Pearson statistic for the simulated data set. Denote the statistic as x squared star to help differentiate it from our original x squared that was observed on the actual data itself. And I'm going to repeat steps 1 and 2, capital B times. I could do a plot of my x squared stars, a histogram of them, that essentially represents an estimated distribution then for the x squared stars. Or in other words, I should say, the estimated distribution of x squared under the null hypothesis. Then if I want to calculate the p-value, basically look at the proportion of times that the x squared stars are greater than or equal to the observed x squared. That's my p-value for my test. So let's take a look at this now with respect to the fiber-enriched cracker data example. So here's the data that we saw previously, and the data is in fiber.csv. We'll read it in. Remember, we had to do a little bit of work to get the data in the correct form so that the rows and columns are ordered correctly. And so this is just taken out of what we've seen before to do that. And if I wanted to, with this now contingency table here that I formed from the xtabs function, I could apply Fisher.test to it. This gives me my Fisher's exact test, and notice my p-value 0.06636. What this ends up doing is using what's called a multiple hypergeometric distribution to apply this test rather than the regular old hypergeometric distribution. The actual form of that multiple hypergeometric distribution is shown in my book if you're interested. So p-value 0.0664. And when we did a Pearson chi-square test for independence in the past using a chi-square 9 distribution approximation, we get about 0.05. So we can see that we get very similar results. Now to do the permutation test, we're going to look at 2 different ways. One way is to use the chi-sq.test function. There happens to be an argument in it called simulate.p.value, and if you set that equal to true, it does a permutation test. So I can set it equal to true, and also there's a B argument that corresponds to the number of permutations that you're doing, the number of contingency tables that you're forming. And when I do that, notice R says, okay, simulated p-value. Here's my original x squared statistic. There's no degrees of freedom here because we're finding the exact distribution. We're not using a chi-square distribution with it. And here's my p-value, 0.039. Very similar to what we had previously. Now, I use 1,000 permutations here. You might be wondering, well, is 1,000 enough? Well, what we can do is actually go back to some stuff that we did in chapter 1 to examine that further. Because as you might expect, if I were to, let's say, redo this permutation test and use a different C number, I'm going to get a different result. Now, I know that since B is fairly large here, my result shouldn't deviate too much, but it shouldn't be exactly the same. So what we can do is think of this 0.03896 as essentially coming from a sample of 1,000, a sample size 1,000, and going back to chapter 1, how about we call that pi hat? And then we use that to form a confidence interval for what the true value of pi is, which would be the true p-value if one did all possible permutations. Okay, so let's do that. So I'm going to reproduce what I had just done. I'm going to save the results now into save.p. Then from the binom package, I'm going to use my binom.confident function so that I can go ahead and find the confidence interval. I'm going to use a Wilson confidence interval. And let me come over here to 10 to do this. Let me come back up here. Oops. So let me run that segment of code that we just talked about. Now, binom.confident. I need to put in for my first argument essentially the number of successes. A success in our particular case corresponds to the number of times that x squared star is greater than or equal to the original x squared. How do I know what that is? Well, in save.p, there's a p-value inside there, 0.03896. So if I combine that or multiply by 1,000, this tells me essentially how often I had an x squared star that was greater than or equal to x. And it tells me 39 times. So I round that result. So it is actually 39. My number of trials is 1,000. Confidence level 0.95. Wilson is my method. Use binom.confident, and this is what I get. So my confidence interval for what the true p-value is 0.029 to 0.053. So my conclusion would not change based upon this. I have marginal evidence against the null hypothesis of independence. So I'm satisfied with only using b equal 1,000 different permutations. Okay. Now, what if you use a larger number of permutations? Well, how about we use 100,000 instead? I could do the exact same process, find a confidence interval for it. So using 100,000 permutations, I get 0.04552 as my p-value. If I wanted to find a Wilson confidence interval for that, I get 0.044 to 0.047. Notice how much narrower that confidence interval is. Why? Well, because I have a larger number of permutations. In other words, a larger sample size. Now, similar to what we did in chapter 3, I would like to actually visualize what that permutation distribution gives us. Unfortunately, the chi-sq.test function does not provide that. So that means that we're going to essentially have to program into R the actual permutation test procedure ourselves so that we can see a histogram of all these x squared stars. And so that's the purpose of this next discussion here. Okay. So to do this, I need to take my contingency table, which was diet.table, change it over to a data frame once again. And so I could have just started with my original data frame diet, but I decided to show you the process here in case you ever run into a situation where you only have the contingency table. So similar to what we've seen before, I can use as.data.frame, and use as.table together. Put the results into set 1. And here is the last 6 values in my new data frame. So for example, for fiber both, bloat high, I had 2 observations. Notice I have some cases where there are zeros as well. Now let me come over here to 10. Now to form then the raw data for this data frame, it's a little bit complicated, but it's not too bad. Okay, so what I want to do is basically, let me actually come back over here and show you. I want 2 rows in a new data frame that represent these combinations of fiber and bloat. I want 5 rows of these combinations. I don't want any rows for brand and high, and so on. So to do that, this is how it can be done. This is the quickest way to do it, although it's also maybe a little bit more of a complicated way. The REP function R allows us to repeat values. And what I want to do is repeat my row numbers in my data set. So just to show you, there's my row numbers. And row stands for number of rows of set 1. If I do 1 colon that gives me my row numbers, 1 through 16. And I want to repeat those numbers, 1 through 16, a number of times. The number of times is the actual count in the contingency table corresponding to when that fiber and that bloat combination occurred. So let me just show you what happens if I run this segment of code. And so we see, for example, if we come down to here, remember we had 2 times we had both and high together. Notice how I have 2 16ths. 5 times I had gum and high together. Notice how I have 5 15ths, row 15 of my original data set. Okay. Now, what I'm going to do now with set 1, left square bracket, I'm going to put all those row numbers into here for the row number part of calling this or referring to parts of this data frame by row and column. I'm going to put all those row numbers in there. So what's going to happen then is going to actually repeat some of our rows. And it's going to repeat the ones that we want repeated. So again, I had 2 times, I had both and high. Look at this. Now I have 2 rows for both and high. I will have, even though you can't see it here, I have 5 times of gum and high because I have 5 right there. I will not have any brand in high or none in high. Then lastly, notice the third column here is freak for set 1. Well, when I ran this code, I don't need that column anymore, so I'm just going to remove it. The way that I can remove it is say -3 there, say don't include 3 or column 3. Okay. Now, just to verify that indeed that this process worked, what I can do is use the xtabs function with the first column of set 2 and the second column of set 2, and I get my original contingency table that we saw before. I can apply the chi_sq.test function with this if I want to. The way that that is done, the first entry corresponds to the row number. The second entry corresponds to the column number. Correct equal false because I don't want that correction that's done by default. Put the results into s.sq. And if I just pull out the Pearson statistic itself from x.sq, this is what I get. I get the 16.94 that we actually had observed before when we first was looking at the fiber data. Okay. Next, let me come over here to Word. Now I want to do one permutation of my column numbers to show you how it's done. Once we understand how to do that, we're going to apply the same technique, basically b equal 1,000 times, so we can get the distribution or estimate the distribution of x squared star. So let me come on over here. So I'm going to set a seed so I can reproduce my results. Then I'm going to create a new set 2. I'm going to call it set 2 star because this is going to be based upon my permuted column numbers. And what I'm going to do is take my data.frame function. For my row variable, I'm going to just simply put in the first column of set 2. But for my column variable, what I'm going to do is sample from these column numbers with replacement. So just to show you how this works, let me just execute that small segment of code. And so now this is essentially a random permutation of all those column numbers. Another one, another one. It just so happens that well, let me just come back up here. Yeah, that's right. So we can see this is how we can permute the column numbers or the column level names. Basically, it's going to mean the same thing for us. Okay, so if I put the original row numbers with the permuted column numbers. So here's what we have. And so if I did set2.star, this essentially is one permutation of my data. I can use X tabs with this to see what the contingency table looks like. If you notice, it's not exactly the same as what we had previously with the observed data. I can calculate the Pearson chi-square test statistic with this permuted data as well. And I get 14.64. Again, not the same as what we had previously with the original data. Okay, so now that we see how to approach this in terms of one permutation, let's repeat this capital B times. So to do this, I'm going to set B to be 1000. Then I'm going to create a matrix where I'm going to store all my x square stars in. So x.sq.star.save is just a matrix that has B rows, one column. I'm going to initialize it with NAs. And eventually what I'm going to do is put for permutation 1, I'm going to put x squared star in there. For permutation 2, I'm going to put x squared star in there in the second row. So let me go ahead and execute that. And so that I can reproduce my results, I'm going to set a seed. And then let's repeat the following capital B times. Exactly what we did before. I create a data frame that has my permuted data in it. I calculate x squared for that data frame. And then I save now the results into the ith row of my data frame that's going to save my results. So let me go ahead and do this. And if I were to look at x.sq.star.save, what we're going to see here is that we have 1000 of these x squared stars. I want to find the proportion of these x squared stars that are greater than or equal to my original x squared. So here is a bunch of trues and falses corresponding to, is x squared star greater than x squared? So for example, 974th x squared star is actually greater than that. Then when I use the mean function with that, r is going to take the trues, make them ones. It's going to take the false, make them 0. And the mean of 1s and 0 ends up being the proportion of times that x squared star is greater than x squared, and I get 0.039. That's my p-value for my permutation tests to test for independence. Okay, let's go back over here to my file, my Word file. On your own, I want you to see this function I've created called summarize, which will automatically calculate the p-value, but also do 3 plots of interest. Let's take a look at those p-values. I'm sorry, take a look at those plots. So, I guess just to make sure you see how to run this function, summarize, I put all my x squared star saves, or I put all the x squared stars, I should say, in my argument called result.set. I put my original test statistic value in there for statistic. My degrees of freedom ends up being the number of rows minus 1 times the number of columns minus 1. That's what I would have for degrees of freedom for using a chi-square distribution. And then I'm going to state, well, what was actually B. So the first plot that's generated from this function is a histogram. And it's scaled so that I can plot the actual chi-square distribution upon it. My x squared stars are on the x-axis. And what we see in this histogram is that the red plotted distribution, it's a chi-square 9. It follows a very similar shape to the histogram, and therefore a chi-square 9 distribution does do a good job of estimating the distribution of x squared. This is similar to what we have found previously when we did that Monte Carlo simulation-based test in Chapter 3. We could also then look at a cumulative distribution function. So the chi-square 9 cumulative distribution function is in the red dots. The empirical cumulative distribution function is what's shown in black. This is for the permutation distribution itself. Just to review what an empirical or ECDF represents, here's x squared star 10. What that's going to do is calculate the proportion of times where x squared star is less than 10 for these x squares. X squared star 5 represents then the proportion of times that an x squared star is less than or equal to 5. Again, empirical cumulative distribution function. And we can see here is that this permutation distribution follows very closely to the chi-square 9. Lastly, here's a QQ plot. If you haven't seen a QQ plot before, let me briefly explain it. Q stands for quantile, so it's a quantile plot. And what this is as follows. Suppose you order all your x squared stars. Okay? Now, the smallest of those x squared stars, essentially, let's say, is the 1 over 1,000 quantile from your x squared star distribution. The second smallest is the 2 over 1,000 quantile from your x squared star distribution. Now let's plot those values against the corresponding quantile from a chi-square 9 distribution, meaning use, let's say you're using the q chi sq function. The first time that I would do this, I would use 1 over 1,000 with the degrees of freedom of 9. The second time, I would put 2 over 1,000 with the degrees of freedom of 9. So it's finding then the corresponding quantiles for this chi-square 9. If a chi-square 9 distribution is a good approximation for the distribution of x squared star, what we would expect is all the plotted points basically to fall on a line drawn at a 45-degree angle from the origin. Why? Well, what this is basically saying is that my quantile of about 10 for a x squared star should be about a quantile value of 10 for the chi-square distribution. That's why. And so what we can see here is a very close job or close approximation. We see a little bit of a deviation here, but not much at all. And that often happens with these QQ plots anyway. Okay. So what we have concluded is that there's marginal evidence against the null hypothesis of independence for this fiber data set when we treat the bloating variable as a nominal categorical variable. Also, I guess I should say, also we found that the chi-square distribution approximation actually does well too. Now, here's a question for you. How could we find estimates of the distribution of x squared, meaning find the probability that x squared is equal to a particular value that it can take on? How could I do that now with the information that I just got from doing this permutation test essentially by hand with the help of R? Well, what we could do is as follows. Let's see now. So all of my x squared stars are in x.sq.star.save. And so what I could do is do table x.sq.star.save. And what this is going to give me is how many times did I have a 29.62? Well, I had it only once. So the probability of that occurring, at least from doing 1,000 permutations, is 1 over 1,000. Let's see, I can keep on going up here. Eventually I'll hit a 2. So the probability that x squared is equal to 13.58 is 2 over 1,000. So that's how I would find it. And what we can see in this particular case, since we had a larger contingency table, we had a larger sample size, we have a lot more values of x squared compared to what we had with the lady tasting tea example. Okay, so some final comments here. These permutation tests are used in a wide variety of situations beyond just simply testing for independence in a contingency table. Typically where these permutation tests are talked about extensively are in computational statistics courses or non-parametrics statistics courses. Now, what about a situation where we can see that indeed a chi-square approximation doesn't work very well? Well, on your own, I want you to work with this particular contingency table that comes about from the code that I have there. And you will see that indeed the appropriate chi-square distribution approximation does not work for this situation. Okay, so that concludes this section on using permutation tests.